Right, now that we've looked at components and we've worked out normal force and friction force, we are ready to start with Newton's laws. Now, if we look at Newton's 3 laws of motion, number 3 is very different to number 1 and 2, and we are going to focus on that in another video. I want to focus now on Newton 1 and 2. They are two sides of the same coin. To start with Newton 2 tells you if there is a resultant or a net force working on an object, what happens to that object? It will accelerate, and accelerate means it will have a change of velocity, right? And the acceleration is actually how fast the velocity is changing. So you'll definitely have a changing velocity. A net force will always cause the velocity to change. It will cause acceleration, right? And then we will also learn how big the acceleration is. But to focus on Newton 1 is the other way around. If a net force causes acceleration, then if there's no net force acting on an object, that force will not accelerate, which means the velocity will not change, which means it will either be standing still or it will be traveling at constant velocity. So immediately if you have acceleration, then you are working with Newton's second law. If you have zero velocity or you have constant velocity, then you're working with Newton's first law. And obviously you have to know the definition. A body will remain in its state of rest or motion at constant velocity unless a non-zero, right? As long as there's no F net, right? Unless there's a net force, because then we will be moving on to Newton's second law. Right, now type of questions that we can expect here. 1.5, a crate of bananas is on the back of a moving truck and the truck stops quickly and the crate keeps moving forward. Use scientific principles to explain this phenomenon. Now, it was moving, right, and it keeps moving, right? So this is actually a Newton 1. Now, if they tell you to use scientific principles, you definitely have to tell them which principle you're using. I'm using Newton 1. And when you have to formulate an answer, remember if I'm working Newton 1, I have to try to use the formulation in there, right? So I will try to think about what the definition is or what the law is, and then try to use the same concepts. Now, a body. Now, don't write a body, right? We're definitely not working with a body. We're working with actually the crate, right? The crate. And what does Newton 1 tell you? That the crate will remain in its state, and don't say rest or constant motion. This one was definitely not in rest. The crate will move, will keep moving, right? It will remain in its state of constant velocity. So the crate will keep moving at, and now velocity has got magnitude and direction, right? Magnitude, the speed, how fast it is going, and in the same direction. It will keep moving at the same speed, okay, at the same speed and in the same direction. Right, and let's just look at the second part of the definition. Unless a near zone, okay. So we have to tell them it's doing this because no net force is acting on this. No net force is acting on it. Right. So the crate will keep moving at the same speed in the same direction. It will not be changing velocity because we don't have a net force. Right. Now, it could have changed this. If that driver put a rubber mat on the back of the truck, then that might have given us frictional force. That could have been the net force that would have stopped this crate. Right. Now, you can also explain Newton 1 in terms of inertia, and sometimes we call that the law of inertia. Now, remember with inertia, it's not a force, it's a property of matter, right? It is the resistance of any physical object to any change in its state of motion, right? So it doesn't want to change its state of motion. And this includes speed, direction, and rest, right? And the tendency of an object to keep moving in a straight line at constant velocity. So it doesn't want to change its motion, right? And then they say something important: mass is a measure of the amount of inertia. So the bigger the mass, the more it will resist changing its velocity. And that makes sense, right? You will have a much harder time pushing an elephant than pushing a mouse. Right, let's look at this one. So I can also explain this in terms of inertia. And there I will say the crate has mass, and therefore inertia, and it will resist changing its movement. It will continue moving at constant speed in the same direction. Right. Now let's apply this to another question, and that is question 1.6. They tell you 2 ropes are tied to a heavy crate. Heavy crate, immediately tell me a lot of mass, big inertia, right? Tells me the crate doesn't want to change its movement. And what is its movement at the moment? It's hanging still, so it doesn't want to change the fact that it is in rest. Now, one of the ropes is tied to the ceiling and the other one is hanging down. And now the question is, if the lower end of the rope is pulled quickly, and in the next question, if it's pulled slowly, which rope will break? And explain this. Now, if you pull it quickly, remember this crate has got a big inertia. It's got a big mass. It doesn't want to change its movement. And that means this one will break at Y. Right, because of the big inertia of the crate. Right, the big inertia of the crate causes it not to change its movement. So it stays in rest and the rope at Y breaks. Next up, the lower end is pulled slowly. Now, if they pull it slowly, then it will break at X, and that is because the X has got the bigger tension. Right. It's got that pulling down there, and it's got the weight of that crate pulling on X. Next up, we're going to look at 1.7. In the following diagrams, force vectors are drawn head to tail, and you are asked to draw the resultant force in each diagram. So in this diagram, it's going from there to there. Remember, it's starting where all the others started and ending where they ended, right? So that's R. In this one, it's going from there to there. That will be R. Starting where they start, end where they end. This one, it looks to me, it looks the same like the first one. Okay, R. And in this one, okay, so there's no room for a resultant force. So here F net is 0. There's no room to draw a net force, right? So if you get them and they give you a closed figure, then you have to know that that is F net 0. So here I've written it down for you. We call that forces in equilibrium, right? If an object is in rest or traveling at constant velocity, then there's no net force, right? We say the forces are in equilibrium and F net is 0. And immediately, if you do a head-to-tail drawing, then you end up with a closed figure, right? This is important because we're going to use that in the next applications. Right, so let's look at this one. Forces in equilibrium. So they tell you they've got a parcel with mass 50 gram, and that hangs. Now immediately that word hangs is going to tell you this is in rest, right? And if it is in rest, I'm working with Newton's first law. It tells me F net is 0, right? Now it's hanging from a rope fixed to the ceiling. The rope is supported by a beam S, right? Determine the tension in the rope T and the force exerted by the beam on point P. Okay, take it, that's one. Right, so with this, there's a number of ways that we can do that, but all of that depends on knowing what the forces, the direction and the magnitude of the forces. So let's look at point P. At point P, that's where all the forces are working on the same point, and we know that that point is in rest, so F net for all the forces on that point should be 0. And that means if you look at all the forces, now what do we have there? We have gravity pulling that one down. This is a rope, and remember a rope is pulling on both sides. Always a rope is pulling. So you will have T in that direction. And then we have to look at S, and we have to say, okay, what is the direction of S? Is it pushing in that direction, or is it pulling in that direction? Now, if you have a problem understanding this, let's keep our eye on that spot and we remove F. If I take S out, what's going to happen with that? And I think all of you will agree it's going to swing inwards, right? So S is actually working in that direction, keeping it from swinging inwards, right? So S is in that direction. Now, when I want to work with this, I may work with components. We're still going to look at that, or we can make a drawing and use that. Now let's just see how a drawing of that is supposed to look. Now, you can take any vector to start with. I usually like to take gravity, because gravity, you know exactly the direction of gravity, right? Gravity is easy to draw. But then you can have two different triangles. I can choose to draw S first. Now S is to the right and up. Now this is not a scale drawing, it's just a rough drawing. So I'm going to do S to the right and up, keep the direction the same, and then I'm going to draw P, and that is to the left and up. And what do I know? I must know that if F net is 0, then that means I get a closed triangle, right? A closed triangle. So I make it into a closed triangle. I draw it so that it makes a closed triangle, right? Or remember, we could have done it the other way around. You could have chosen to do T first, which is to the left and up, and then S after that to the right and up, and once again make it a closed system. Right, looking at this, you have to have the angles in there. So let's think about T. If you look at T, they give us the angle between T and the horizontal. Now there you've got T. Let's go and draw in the horizontal and add over there the 40-degree angle. Right. How about S? For S, they give us the angle with the vertical, which is nice because we've got the vertical in there. So there they have that 60-degree angle. Now, guys, this one you have one or two ways to use. You can either do a scale drawing, right? Now, for a scale drawing, this is not very accurate and it is very time consuming. So we don't like to do that really a lot. But here, I will start by drawing gravity because I know exactly the magnitude and the direction. So if I know magnitude and direction, this is the one I'm going to draw first because that's going to give me 2 points where I can add the other ones. Right. What do I know with T? Well, I've already done my quick rough sketch, and that tells me that it has to end up there and it has to be at a 40-degree angle. So I just draw it, and I draw it long line in that direction, ending at that point. Right. What do I know about S? 60, so I'm going to measure that and I'm going to draw a long line in the right direction, and there where they cross each other I will know S is ending over here and T is starting over here. And then we go to measure S and we get to measure T and convert back according to the scale. Right, but we are not going to do a lot of that. what I'd rather do is use that rough sketch, not to scale, and the sine rule. Right, now sine rule, a over sine A is equal to b over sine B, and that is equal to c over sine C. Now that is not prescribed by the Department of Education. You don't need to do this, but it is a nice way and often a very fast way to do things. So let's look at this one. Now, if I have my drawing, and now I have the 60 degrees down here. If that is 40, then obviously that is 50, because together they make 90. And if I've got 50 and 60 gives me 110, then this one should be 70 degrees, right? So I've got the inside angles, and that's what I'm looking for. Now, when we have to put in A, B, B, and C, C, I'm going to use A for the one that I know everything about. Now, I've already know the mass and the force of gravity here, so I'm going to call that small a, and then the angle at the opposite will be the capital letter A. And then I can choose any one for B, right? Lower caps letters we use for the sides, and capital letters for the angles. And then this one will be C, and that will be angle C, right? So A over sine A, right? I've worked that out. 490 over sine of 70 is equal to B, that is T that we're looking for, over sine of 60. And then you work out the answer. Now, A over sine A, exactly like before, but now C, which is S, divided by sine of 50. And then you get the answer. Right, so that is if you use the sine rule. But what you also need to know, and definitely need to know, is how to work with components. Now, the important thing is if forces are in equilibrium, if net is 0, that means if you look at all the x components, they must be 0 altogether, and the y components must be 0 altogether. You can't have an x component, because then that would have been the answer for F net. You can't have a y component, because that would have been the answer for F net. Or if you have both an x and a y component, then obviously there was an F net. So you need to have no answer in the x direction and no answer in the y direction to get an F net of 0. So first off, we're going to resolve the forces into components. So you're going to take x, S, over there, and we're going to say, let's replace S with an S in the x direction and an S in the y direction. Right, and remember, if we want components, we want to work with the angle with the horizontal. So I'm going to work with that 30. Right, let's take T. T over there. I'm going to replace that T with a T in the y direction, T, y, and a T in the x direction. Right, and now what do I know? All the components in the x direction should add to give 0. So in the x direction, to get a 0 answer over there, that tx should be equal to sx, right? And how do I work out tx? T, now it's the whole force T that I don't know, I'm looking for that one, times cos of the bottom angle. Well, I've got that 40, and it is an alternating angle with this one, so that will be 40 as well, right? Times sx, which is the whole s times cos the angle with the horizontal. Now, you can't get an answer for either s or t, but you can get an expression that we can use. Right, next up, in the y direction, up and down, F net must also be 0. So the only way for F net to be 0 is if all the ups are equal to all the downs, right? So the gravity will be equal to Ty and Sy. Now, gravity, that's just 50 times 9,8, right? They gave us 50 kilograms. And then T will be T, and now remember we're working with the y component. I'm using the correct angle, so this is going to be sine of 40, right? And for the S one, that will be the whole S times sine of 30. Right, and then we've already worked out an expression for s. For s over there, we've said s is equal to that, so we can replace that s with that whole expression and then solve for t and then put back into that one and solve for s. So guys, this is not impossible to do. Just make it into components, right? Resolve it, and then all the x components together must be 0 and all the y components together must be 0. Now you have to do one, and that is the one on the next page. Determine the mass, so this is the unknown, and the angle theta up there with two different methods. So even if you haven't done the sine rule before, try to do it with both the sine rule and with components. Right, in this question, the first thing you had to do is to say everything connects at that point. So the forces over there were gravity, it worked down. You've got a rope, so a rope is definitely pulling. This one, I don't know if it's a rope or a beam. Let's think, if I remove this, what is going to happen to that point? It's going to swing this side, so that is actually preventing it from swinging back, so it is in that direction. Right. Okay, now for the sinus rule, I need to draw a triangle. So I'm going to just draw, and remember it's not to scale, so just start drawing. So you've got gravity, then choose one. I'm going to choose B next. What do I know about B? B is going to the right and up, so to the right and up. There I have B. Then T, what do I know? T is going to the left and up, and since this one is hanging still, I know I'm working with Newton's first law, and I know F net is 0, and I know if I've got a diagram, I need to have a closed figure. So I will make it so that it is a closed figure. Right, but this is just a rough drawing, it's not to scale. Right, next up, let's go and write in. We have the T is equal to 300 newtons. We have the B, that is equal to 200 newtons, and we also have that 40-degree angle. That is between B and the horizontal, so between B and the horizontal. Now, it doesn't matter if it's up there or down there. Remember, it's alternating angles, right? So that one is 40 degrees over there. Right, now for the sinus rule, we actually need the inside ones. Okay, that one, they're asking us for theta, and theta is over there, so we don't have that one. That's also an unknown. But I know this 40, so that means I know inside this will be 50. Right, now I have to decide which is A and B and C. You can use any one for A and B and C. I like to use A for the one where I know both the force and the opposite angle. Right, and then let's work with this one for B. It's already called B, and then that angle will be angle B, and if I call this one C, that angle will be angle C. Right, so A over sine of A is equal to B over sine of B. A over here is that 300 over sine opposite angle, sine of 50, and that will be equal to 200 over the sine of B. Right, and then you can solve for B. Right, now if you solved for B, you should have got 30,71 degrees. Now that 30,71 degrees is not the answer to theta yet. Remember, theta was the one with the horizontal, and we've now worked out that B, which is the one with the vertical. So if you are looking for theta, that will still be 90 minus that 30,71, which is 59,29 degrees. Right, so we've solved one of our questions. The next question was to work out the mass. Right, so looking at this one, now I'm going to work with A over sine A is equal to C over sine of C. Right, now A over sine A, I've already done here. Let's just write it down. 300 over the sine of 50 equals C, and that is the gravitational force that I'm looking for over the sine of, and now I need angle C. Now I've already calculated B, so C is going to be 180 for all the inside angles, minus the 50 down there, and minus the 30,71 that I've already calculated up there. And if you do that, you end up with 99,29 degrees. So this is what's going in here, 99,29. And then for gravity, you can work out gravity, or you can just replace 9,8 times m over that sine of 99,29, 300, and sine of 50 degrees, right? And when you solve for m, you end up with 39,45 kilograms. Right, so this was when you use the sine rule. First, you have to draw a triangle, rough, but you have to have the angles and all the variables that you know. Right, next up, we're looking on components. And for components, we are going to not draw a triangle. We're going to do a force diagram. We're going to say we've got B in that direction. What do we know about B? B is a 200 Newton force, and we actually have the angle with the horizontal there. And I will throw that B away and replace that B with a B in the Y direction and a B in the X direction. And then I'm going to take T. T is in this direction, and I'm going to replace that T, that is a 300 Newton force, with a T in the Y direction and a T in the X direction, right? And then you still have gravity down there. Let's add that one, right? And now what do I know? If F net is 0, that tells me that all the X components together will add to 0, and all the Y components together should also add to 0. Right, so looking at the X components, the only way for this to be 0 is if Tx is equal to Bx. Right, now let's replace T. What do I know about T? Now, I've got no angle there. Let's go back. Okay, the angle with the horizontal between T and the horizontal is actually theta, and that is one of my questions. I have to work out theta. So here, how do I work out the X component? It will be the whole force T, which is 300, times cos for the X component and that bottom angle that I don't have. Right. And next up, that will be 200 cos 40. And that means I can solve for theta. And if you do that, you end up with 59,34 degrees, right? Pretty much what we got in the previous question as well. Right, next up. For the Y components to be 0 means all the ups is equal to all the downs, right? So Ty and By will add to give the same as gravity, right? Now, how do I get the Y component? That's the whole T, and for Y, it will be sine of that angle. Now, I know what that angle is, 59,34 degrees, plus B, and that is now, I can replace that B, that is 200, and that is now sine of 40. And altogether, that is going to give me 9,8 times m. And now m is the unknown. And if you solved for that, I hope you all got 39,45 kilograms.